Welcome Algebra 2 students to our video notes lesson on section 6.6, where in this video we will learn a little bit about inverse relationships. We'll get introduced to inverse relationships, and then we will spend most of our time focusing on how to find inverse functions graphically. Okay, so hopefully you had a chance to complete the Desmos investigation before watching this video. And hopefully you were able to make some observations, just an informal observation about what an inverse relationship is, what it does, just through walking through that Desmos activity. And here I just want you to kind of state informally what you observed. So hopefully what you observed was that an inverse relationship, in a sense, cancels out or undoes or reverses the operations of the original function. So to maybe sort of give you a visual sense of that, suppose we have like this set of values. We're going to call it the domain, right? These will be our inputs. And then they get mapped onto this set of values. We'll think of that as our range. We also refer to that as the outputs. So let's suppose there's this element, we'll just call it A, in the domain. So the f of x function comes along and says, okay, I'm going to take this element A, I'm going to do some stuff to it. So this would be the f of x operations. It just depends on what's in the equation. Are we multiplying it to something? Are we square rooting it? Are we dividing by it? That's what the f of x function tells us. And then it brings it and turns it into some other value that we'll call b. So that would be like our output. So suppose that's f of x. Well, then the inverse of f of x comes along and says, okay, I'm going to take this element b from the range. It grabs values from the range instead of from the domain, and it maps it right back to A. It does all the reverse operations of f of x. So when f of x added, inverse of f subtracts. When f of x square roots, inverse of f of x squares. When f of x divides, inverse of f of x multiplies. So the inverse just basically undoes all the operations that f did and brings us right back to our starting point. So it sort of, in a sense, cancels out everything that the f of x function did. So we could say that if I take the inverse of f, which we use this little -1 notation. We'll talk more about the notation in our next lesson, but for right now, this just stands for the inverse of f. And I take my output values from the f function, it'll map them right back to the beginning. So f of x would take the a value and bring it to b. F inverse would take the b value and bring it right back to a. So we could say that the inverse function switches the inputs and outputs from the original function. Okay, so that's an informal observation. They switch. X and Y switch, or A and B switch. Input, output switch. Now, the formal definition is what I'm going to give you now, because it's good to know how things are said formally. It's basically going to say the same thing, but in a much more formal way. So let's begin. So formally, we would say, if an original relation pairs element A of its domain to element B of its range, then its inverse pairs B with A. We sort of just saw an illustration of that. So if an original relation, maybe we'll think of that as our f of x, pairs element A of its domain to element B of its range, we can think of this part as the f of A equals B scenario. So I plug in A, the domain, the A is the input, the B is the output. So that's domain, that's range. So the original function does that. Then its inverse pairs B with A. So this was the example from before where we then had this other function, this little -1 function, and now we plug B in there. So now B is the domain and A is the range of the inverse function. It goes backwards. It reverses the order of f. So then we could say if the point, this is the ordered pair AB, if the point AB is a point of the original relation, then BA is a point of the inverse relation. Sorry, I ran out of room there, I had to squeeze it in. But again, if an original relation, we'll call it f of x, takes A from the domain and pairs it to B from the range, so that could be demonstrated by this blue function here. It was taking A and doing some stuff to make it turn into B. That was our f of x function. Well, then the inverse relationship will just take B and pair it with A. It'll reverse the input and output. It'll reverse the domain and range. It'll reverse the order of the ordered pairs. So if AB is a point on the original function, BA would be a point on the inverse of f of x. So again, informally, the inverse function just undoes or reverses the original function. And formally, we say it switches domain element and range element. Okay, so let's think of some examples of functions we've already studied that have this inverse relationship with one another. So the first one for me that comes to mind is the squaring relationship and the square rooting relationship. So for the x squared relationship, my domain elements could be like 1, 2, 3. And if I apply the squaring function, then I square those numbers, 1, 4, and 9. That's the squaring function. Well, then the square root function does the reverse. It takes these numbers, square roots them, and brings them back to these numbers. Square roots the 4, brings it back to 2, and so on and so forth. So these are what we could say are inverse relations. Another one that comes to mind is cube rooting, cubing and cube rooting. And for a very similar reason. So again, I'll take those numbers 1, 2, 3. If I apply the cube function to them, the cube will take the 1, cube it and get a 1. It'll cube the 2 and get an 8. It'll cube the 3 and get a 27. So these are the outputs when you cube the inputs. Well then, the inverse would be cube rooting. Cube rooting, these numbers will take you right back to where you started. If I cube root 1, I get 1. If I cube root 8, I get 2. If I cube root 27, I get 3. So a cube root will undo a cube, and vice versa, which is why we're able to use these to solve equations. And then another one, which may not be as obvious, although I'm hoping some of you thought of it, would be like an exponential versus a log. So I could have maybe the function 2 to the x, and then the function log base 2 of x. So in that scenario, if I'm applying the exponential function, then these numbers over here, 1, 2, and 3, these would be powers of 2. So my outputs would be 2 to the first power, 2 to the second power, 2 to the third power. Well, the function that would go the other way, that would undo that and go the other way, would be a log base 2 of x. The log base 2 of x takes the answer to an exponential problem and gives you back the exponent. So the log base 2 of 2 is 1. The log base 2 of 4 is 2, because 2 squared is 4. The log base 2 of 8 is 3, because 2 to the third is 8. So an exponential function and a logarithmic function, if they have the same base, so that's important, will basically cancel each other out or undo each other because the log is doing the reverse of the exponent and vice versa. So we've looked at informal, formal definitions of an inverse, and then a few examples with our functions. Now, one thing I want to point out though, is it turns out that not all inverses of functions are also inverses. So that's important for us to understand, which is why I keep using the word relation. So sometimes the original equation is a function, but the inverse is not. That does happen sometimes. And this happens when you find the inverse relationship and it doesn't meet the criteria for being a function. So we have to remember what the criteria is for being a function. So to be a function, a relationship must pair each input with exactly one output. So that means you can only have one y value for each x. And sometimes when you take the inverse relation of a function, it doesn't meet that criteria. Now, when you're looking at it graphically, it has to passes the vertical line test. If a graph doesn't do that, that means there's more than one y for each x, which means it's not a function. So we're going to have you find the inverses graphically, but then determine if that inverse is a function or not. If it is a function, we're going to want you to try to figure out which function it is. Now, I want to let you in on a little secret. We can tell if the inverse is going to be a function if the original function is 1-to-1. So if your original function is 1-to-1, your inverse will definitely pass the vertical line test. So what does it mean for a function to be 1-to-1? It means it pairs each input with exactly one output. So it does that, same thing as a regular function, and also pairs each output with exactly one input. So in other words, it works the other way too. That means one y for each x and one x also for each y. Now this type of graph would pass both line tests, the vertical and the horizontal line test. And as you might recall, not all of our functions pass both. They all, of course, have to pass the vertical line test to be functions, but not all of them additionally pass the horizontal line test. If they do, then their inverse, once we find it, will guaranteed be a function. Their inverse will guaranteed pass the vertical line test. Okay, let's take a look at one example where the original equation is a function, but the inverse is not. So the classic example of that would be the quadratic function. If you recall, the quadratic function has the graph of a parabola, and so it does not pass the horizontal line test. It crosses at 2 points. But let's go ahead and sketch this graph. So this is, the parent function is a quadratic. I'll do that over here. This is the parent for a quadratic, where the y value is just x squared. So I'll just use these points. And I get 4, 1, 0, 1, 4, just from squaring those x's. Then I'm going to add 5 to the x's and 3 to the y's. So this table right here will be the points for this graph that I'm being asked to graph. So that would be 3, 4, 5, 6, and 7. And then this will be 7, 4, 3, 4, 7. So now I'll plot these points here. Okay, so there's my graph of this function f of x. Notice how it is breaking the horizontal line test. So now we're going to find the graph for the inverse. So the inverse is where you switch x and y. So basically what I'm going to do is take this table and reverse the order. So where it was 3, 7, now it's going to be 7, 3. 4, 4, well, that one stays the same. 5, 3 becomes 3, 5. 6, 4 becomes 4, 6. And 7, 7, well, that one stays the same too. So this will be the inverse because I'm basically just reversing the order of x and y from the original function. So you probably are noticing that the inverse graph ends up being like a sideways version of the original graph. You just switch the ordered pairs and then you see this kind of horizontal parabola or a parabola facing right instead of facing up. And so notice that because of that, because the original function failed the horizontal line test, well then the inverse, because it's flipping x and y and switching everything sideways, will definitely fail the vertical line test. So this inverse relationship, it's still a relationship between x and y. It's just not a function because now there are multiple y values for the same x. So here I have a y value of 3 and a y value of 7, both being paired with the x value of 7. So not a function. So that's why. That's why if the original function is not one-to-one, that's why the inverse will not be a function. So it's something we want you to keep in mind. Now, before we actually get into the examples, I want to give you this fun fact, and that is graphs of inverses are going to be symmetrical across the line y equals x. So they're reflections of each other across that line. So it makes for some very pretty pictures, but also it's another way for us to decide if two functions are inverses of each other or not. Because if they are, they have to have this symmetry around this diagonal line of y equals x. Okay, so let's kind of summarize what we learned about how inverse functions are related and what we can use in order to find the inverse graphically. So basically what we realize is that to find the inverse graphically, we just need to switch the order of the ordered pairs for the original function. So in other words, if your original function has the point a comma b, the inverse will have the point b comma a. So we just reverse x and y, reverse the domain and range. Then we can check to make sure that our two graphs have symmetry. Have symmetry across that line y equals x. If so, then they're inverses of each other. Okay, so let's try out some examples. So first what it wants us to do is identify what the parent function is and then what type of equation it's written in and graph it. So we're going to start with f of x. Then we're going to go ahead and find its inverse. We're going to use a different color, graph the inverse, and then we're going to determine if the inverse is a function, and if so, what type of function it is. So for this first example, this equation here is a linear equation, and it's in slope-intercept. So it has a y-intercept of 2 and a slope of -1/2. Because when you're in slope-intercept form, the number in front of x is your slope, and then the number added to x would be the y-intercept, the point where the line will cross the y-axis. So when I plot that, I go up to 2 on the y-axis, and then this would mean I'm going to go down 1 and then to the right 2. That's what it means to have a slope of -1/2. Down 1 and to the right 2. And then maybe I'll do a couple the other way, so I could also go up 1 and left 2. Just to get a lot of points on my original function. And then I'll connect these. Okay, so let me just make a little table of values really quick. So I know I had 0, 2 in there. And then let's take a look at this one. That's at -2, +3. And then maybe we'll also take a look at this one was at +2 to the right 2 and up 1. And then to get my inverse function, I'm going to switch x and y, flip-flop x and y. So now x will be 3 and y will be -2. X will be 2, y will be 0, and so on and so forth. And then I'm going to plot these points. And I notice that my inverse function seems to be going down 2 and to the right 1. So I can maybe continue that process in both directions. So there's the graph of my inverse. Here's my original function. Call that the f of x. And then this is the inverse graph. So things to remember. Y equals mx plus b is a linear equation. M is slope, b is the y-intercept. To get the inverse, switch x and y to graph inverse. Okay, then I want you to graph the line y equals x, which is basically a diagonal line. It's basically in slope-intercept form, so it has a slope of 1, and it passes through the origin. So basically it cuts quadrants 1 and 3 in half. Cuts them in half, so it just kind of goes right through quadrants 1 and 3. Notice that these functions do have a symmetry across this line. Like this part of my inverse is a reflection of that part of my original function. And this part of my inverse is a reflection of that part of my original function. If I were to take one piece and fold it over that diagonal line, it would map onto the inverse. So that's confirmation to me that I did the inverse function correctly. Then for this one, I would say definitely the inverse is a function because it passes the vertical line test. So yes, it happens to be a linear function also because it's a graph of a straight line, and it is a function. So yeah, it's a linear function. So moving on to example 2, and I notice here is another quadratic, which we've already done. So I think actually, and I already changed this on your outline, I think I'm going to instead graph an absolute value function because we haven't done one of those in a while, and it is on your homework. So let's use this for f of x instead. Okay. So here's our second function. What we're going to do first is recognize what type of function it is. So this is an absolute value function. And it is written in what we call HK form, or sometimes we refer to it as vertex form. So for an absolute value function, I'm going to write it down here again. The generic setup for the AHK form is A times absolute value x minus h, and then absolute value plus k. So if I just kind of pair up the A, H, and k values with the numbers in this equation, I can see that A is -1, H is +1, and k is 4. So in an absolute value function, the A is the slope. Or I should say the slope is going to be both positive and -1. That means on the right side it'll be negative, and then on the left side it's positive. And then when you put the HK point together, 1, 4, that is the vertex of the absolute value graph. So I'll start by plotting this vertex. And then I will continue by doing a slope of -1 from there. And then I'll do the same thing on the left side. So on both sides, it's going down 1 and to the right 1, or down 1, in this case to the left 1. So this is the shape of a V facing down, because the a value is negative. So this is our original function. So notice that the original function, once again, fails the horizontal line test. So the original function, which is, this is the parent form of it, the absolute value function, is not 1-to-1. So we're about to find the graph of its inverse, and what you'll notice is the graph of the inverse will not pass the vertical line test. So the inverse relationship to an absolute value is not going to be a function, because absolute value is not 1-to-1. Okay, so to get the inverse, we'll do the same thing we did in example 1, which is where we take some points off of this graph. So I'll definitely use the vertex. So that's 1, 4. And maybe I'll do a couple points on the left and right. So I have 2, 3, and 3, 2. And then on the left, I have 0, 3, and -1, 2. Sorry, a little squished down there. So I just looked at points on my graph and then wrote out their coordinates. For the inverse function, you basically just reverse the order of those ordered pairs. So this point that was at 1, 4 would become 4, 1. 2, 3 would become 3, 2. And then 3, 2 would swap and become 2, 3. 0, 3 would become 3, 0. And then -1, 2 would become 2, -1. So now I'm going to plot these inverse points over here, same grid. So here's 4, 1, 3, 2, 2, 3. So they shared those same points. 3, 0, and 2, -1. Now, it might help for me to dot in the line that I know they're supposed to be symmetric over to help me visualize how to connect these dots. So I need this graph inverse to be a reflection of the original function across this line. So I'm thinking this part is going to keep going this way. So this is a reflection from here. And then this part will go that way. So this line is a reflection of the other line from the original function. So basically, if you were to look at it by itself, it's like a sideways V. It's the downward V that's been flipped onto its side by reversing all the x and y ordered pairs. So hopefully you're noticing that it fails the vertical line test. So the inverse relationship to my absolute value function, so the inverse of negative x, absolute value of x minus 1 plus 4, is not a function. The last two examples are if you're just given graphs, just given a graph, could I sketch the inverse? The answer, of course, is yes, because of the fact that I can take these points from the graph. I don't need the equation. I just need ordered pairs. And I just switch the order of them. So let me make a table of values for the original f of x, the one that I see here. So I see here that when x is -6, y is -4. And then I have a point at -4, 0, -2, 4, 0, 3, 2, 2, and 6, 2. And I'm going to go ahead and graph the inverse by reversing x and y. So now it'll be -4, -6, 0, -4, 4, -2, 3, 0. This one stays the same. And then 2, 6. So I just basically reversed x and y to get these points. And now I'll plot them. So this is a little bit harder, but hopefully you can see by using the symmetry. So it might help also if I put the line so I can kind of see how it's supposed to reflect. So I think this is supposed to go that way, and then that way, and then that way. There we go. And I get what looks kind of like a bug. But basically I get this graph that has been reflected across the line y equals x. This would be the inverse graph of the original, and it is not passing the vertical line test. So this inverse is not a function because of the fact that it has more than one y value for some of the x's. Like, let's see if I can find it. So here I have, so I have an x. I have y values of 2 and 6 for the same x value of 2. So that's why the inverse is not a function. Now in example 4, this gives you both the original and the inverse, and it gives you two graphs. Sorry, it gives you two graphs, and it wants you to decide if they are inverses of each other or not. So the way we do that is by sketching this line, y equals x, which cuts quadrants 1 and 3 in half, and then deciding if these are in fact reflected symmetrically across that line. And I hope that you can see that actually they're not. They seem very much like inverses, because if I were to move this line up here, they do have like a kind of symmetry, but it's not across the line y equals x. So to be inverses, they have to be symmetric across that line y equals x. I should be able to take a point from this function and switch the ordered pairs and have it end up on the other one. So like, for example, this is the point -2, 5. So I should be able to go to 5 and -2 and find that point being on this function, but look, it's not. It's way down here. The function's up here. So no, these are not inverses of each other. Because, just to kind of put it shortly, the points A, B from one graph do not become the points B, A on the other graph. They don't have that relationship where the points on this graph here are just reversed ordered pairs from this graph. It doesn't work. It's not really quite reflected symmetrically across that line y equals x. So the answer here is no, they are not. Anyway, that concludes this lesson, which is sort of an introduction to inverse functions and to seeing their graphs. There will be some practice that hopefully you will get from the sub to practice at home. And then in our next lesson, we'll go more into detail about inverse functions and look at the algebra behind them. Thanks for watching. See you next time. Bye.